Hi and welcome everybody to our live webinar on how to save time in freeze drying. I'm Marco Muri, Business Area Manager Formulation at Büchi Labortechnik, and I'm here today with Dr. Ulrike Weiss, our Application and Development Chemist for Formulation, as well as Mr. Moritz Anushek, who is working towards a master's degree in pharmaceutical science and is currently a part of the terahertz application group at the University of Cambridge. We are very excited to be here and to start our webinar on how to save you time in freeze drying. Ulrike will first offer you some useful information on how to avoid common lyophilization mistakes. Moritz will then give you some tips on how to find suitable endpoint criteria. You will also have an opportunity to ask questions at the end of the webinar. As a quick side note, due to unfolding situation with the coronavirus, we had to make some last-minute adjustments to the webinar. We apologize for any minor disruptions these changes could cause, and we thank you for your understanding. Before we start, I would like to go over a few items so you know how to participate in today's event. Here you can see a screenshot of an example of your attendee interface. You should see the control panel in the upper right corner of your screen. We also want to remind you that your microphones are muted. You will have the opportunity to submit questions to our specialists by typing into the questions panel. You may send your questions at any time during the presentations. We are glad that you joined this session, and we will jump right in now with Ulrike, who will discuss how to avoid common misconceptions in freeze drying.
Thank you, Mr. Moiri. So welcome to the webinar. Let me start with a short basic, what is freeze drying and what is the difference between rotor evaporation and spray drying. Spray drying is at the same pressure, but just by increasing the temperature, while rotor evaporation, we are moving along the phase line between liquid and vapor, as you can see in figure 1, while freeze drying happens below the triple point on the phase line between solid and vapor, and that is 6 millibar, for example, for water. A freeze drying process can be divided in 3 phases: freezing, primary drying, and secondary drying. And now I will tell you about how to save time and make your process more efficient in all of these 3 phases. So we start with the freezing phase, and it's under the motto sample surface, the bigger the better. So here we want to discuss the importance of proper freezing. A sample in a freeze dryer will dry from top to bottom. However, after a while, the vapor needs to move through the porous dried sample. Depending on the structure, this movement is going to be more or less difficult. So there's the problem of heat creation through to kinetic energy of water molecules colliding. Essentially, you can imagine it's like too many people trying to push through one door. This can slow down the process, or it can even lead to melting of the sample. So if you are working with flasks, they should be frozen rotationally, and vials should not be filled completely. In figure 3, you can see the sublimation rate of a shell frozen flask. This is the orange line. So a rotational frozen flask and a bulk frozen flask, the blue line. So essentially just putting the flask as it is into the freezer. The higher surface of the shell freezing leads to almost double the amount of sublimation in any given time. Here we have done the same for a vial. We have put 3 vials, all containing the same amount of an aqueous PVA solution, but with different diameters. So the green line is a diameter of 24 millimeter and a fill height of 330. blue 37 millimeter and 150 millimeter fill height, and the red is 52 millimeter and 76. You can see in table 1 the water loss after 7 hours. So the bigger the surface, more water can be supplemented in any given time. And for the 24 millimeter surface, we could even see that you can see it in figure 4, it actually never really froze and the sample actually melted. Next, I want to have a look with you at primary drying. This is the main phase as well as the longest, and this is where most of the water is lost via sublimation. And I want to talk first about one common misconception, which is the colder the condenser, the faster the process. The drying force in a freeze drying process is the pressure difference between the vapor pressure over the sample surface and over the condenser. The vapor pressure over the sample is depending on the temperature of the sample, and this is directly depending on the pressure in the system, as seen in table 2. The vapor pressure over the condenser depends on the temperature of the condenser coil. An optimal process can be reached by having a delta T of 15 to 20 degrees. So the question is now, how do I get a delta T of 15 to 20 degrees? For that, I would like to show you some figures. Essentially, when the temperature decreases, the vapor pressure will reach a plateau, as seen in figure 7. So the best way to reach a good delta T is to increase the T of the sample by increasing the pressure. In figure 7, you can see a temperature pressure diagram for water with 2 different delta P's, one and that correspond to the same delta P. And as you can see, the lower the temperature, the lower the pressure. Our delta P1 is the red one, is very, very low. While when we increase the pressure, we still keep a delta T of 20 degrees, but the pressure difference is higher. This is also shown in figure 6, where we did an experiment. We let the same sample ran at 2 different pressures, and you can see at 1 millibar, the process is a lot faster, because it is always better to increase the temperature of the sample than to decrease the temperature of the condenser. Next, I want to talk about heated shelves to make a primary freeze drying process more time efficient. So freeze drying is an endothermic process. It means it needs energy. It has been shown that 1 degree can already shorten a process by 13%, while 5 degrees can shorten it by 50%. Heat can be supplied by convection or radiation. This is what happens when you have a flask. That just happens from the environment, or directly by conduction, and this would be to put it on a heatable shelf. In figure 8, you can see an experiment with heated shelves at 20 degrees and not heated shelves. The orange line shows a sample on heated shelves, the blue line on non-heated shelves. In 7 hours, we could see that double the amount could be sublimated when we supplied heat. So this is a way to really save a lot of time in your freeze drying process. Next, I want to talk about a common misconception, that is that one cycle fits all. We often encounter it that people use one freeze drying sample for all of their samples. However, this might lead to wasting time unnecessary. In figure 9, you can see a freeze drying process of PVA in red and trehalose in green in 2 different concentrations. 1% concentration is full lines and 5% is represented by dotted lines. So already you can see that the different concentrations need different time to finish. This is, as I said before, because the higher the concentration, the harder it is for the vapor to pass through the dried sample cake. And what we also saw is that when we use PVA, the it finishes 4 hours earlier than trehalose. If you just use one standard cycle, you would lose, in this case, 4 hours of time. So there's a lot of optimization possible by fitting the cycle to the product. Next, I want to talk to you about secondary drying. So what is secondary drying? In secondary drying, crystal water is essentially evaporated out. Crystal water is water pockets in your frozen sample that couldn't be frozen. So in this step, we will decrease the pressure even further, and we will heat the shelves up more. Essentially, we will turn the freeze dryer into a high vacuum rotor evaporator. In figure 10, you can see a process of PVA and trehalose again being dried with secondary drying step. And in table 4, we measured the residual moisture of freeze drying cycles with and without a secondary drying step. And for trehalose, we can see up to 1% difference in the residual moisture. However, be careful, especially biological samples need a bit of residual moisture after freeze drying to keep the activity of the biological active. So it's not actually always good to get it a moisture content of 0%. Now, we have talked a lot about how to increase the efficiency and save time in a freeze drying process by methods such as increasing the sample temperature or using heated shelves. However, many materials, especially biological ones, will have a glass transition temperature or an eutectic point. Above this temperature, the sample collapses or even melts. The temperature range where that happens is called collapse temperature and can be measured by DSC, differential scanning microscope, or a freeze drying microscope. Hence, one should be careful to not optimize the process in a way that puts the sample temperature above this temperature. In figure 12, we show 2 freeze drying processes of the same sample with a known collapse temperature at -29 degrees. By changing the pressure, we forced one process to run at -17 degrees and one at -40 degrees. Figure 11 shows the sample after the drying is finished. The upper 4 pictures show the sample that was run above the glass transition temperature, or collapse temperature. So you can see that it collapsed. You can see how it essentially pushed itself down to the tray, and you can see all of these little bubbles on the top. When we put the sample under an SEM microscope, we could also see quite a lot of big holes in the structure itself. The lower 4 pictures show the sample run below the glass transition temperature. So you can see the surface is smooth. It is still looking like it did when we froze it, and when we put it under an SEM, it has very nice and regular structures. Another misconception, or that could slow down your process, is the edge vial effect and shelf spacing. So a freeze drying process is often an inhomogeneous process. When a shelf is filled with vials, some will dry faster than others, depending on the placement on the shelf. Figure 13 shows this by showing the sample temperatures of vials outside, this is the red dotted line, and inside, green and blue dotted line, row of a shelf. The outside will always dry significantly faster due to energy from radiation and convection. This is called the edge vial effect, and it can give a false positive of the freeze drying process being finished. Surrounding the vials with the ferrule, here seen in figure 14, will lead to homogenizing of the drying process. This is shown in the red, blue, and green bold lines, so we can significantly make the process more homogeneous. Another common mistake is to increase efficiency by increasing the amounts of shelf. However, if the space in between shelves is too small, the vapor cannot escape properly, and the process will slow down anyway. So I hope that I have given you a few tips for saving time in freeze drying and optimizing your freeze drying better. And with that, I will give again the microphone to Mr. Meury.
Thank you, Ulrike, for this beneficial information. Now I would like to hand over the microphone to Moritz so he can explain the importance of endpoint determination in the freeze drying process. It seems like that we have some problems with getting Mr. Moritz into the call, so I would like to bridge the time with a question to Ulrike that we got through our questions panel. So Ulrike, one question came up that is, how can we actually freeze the flasks rotationally to benefit from thinner product and faster passing of the vapor molecules through the product?
So what we normally do is we use a rotor evaporator with a special Dewar bath, and then we make a cold bath with ethanol and dry ice, and then we rotate the flask into the Dewar bath and freeze it like this. This is quite a good way to do it because it's also very fast, and it can be prepared. If you have a batch, it can be prepared one day, and then you can just put your flasks into a -40 freezer and store them to the point where you want, where the freeze dryer is free and you want to run your process.
Okay, thank you very much for that answer. So that means that you can use a Bucci rotary evaporator to freeze those flasks rotationally.
Yes, you can use the rotor evaporator you have in your lab anyway. Just swap out the normal water bath, the heating bath, with a Dewar.
Okay, perfect. I will check again. Is Moritz available now?
Can you hear me?
Yes.
Hello? Okay, perfect. All right. Yeah, I'm very sorry. I don't know what happened there. I could hear everything, but apparently you couldn't hear me. So my part of the webinar is going to be about comparative pressure measurement. And comparative pressure measurement is a very important technique in freeze drying, which is often used, and it's implemented in many systems, including the lyo-vapor series, which is why I think it's good and important to talk about it. So you can see my agenda. So I'll first start with why do we need endpoint detection? Also, what other methods do we have here? I think many of you will be familiar with this part already. Then what is comparative pressure measurement and how does it work? And then finally, the big part will be on how to find a good endpoint criterion. Is that endpoint criterion then transferable to different samples? And all of this will be about primary drying, so endpoint detection during primary drying. And then in the end, I'll have a short discussion about endpoint detection for secondary drying. So why do we need endpoint detection for primary drying? And here we can think of two very simple scenarios. Well, when we have no endpoint detection, we might have a late change to secondary drying. That means usually no damage to our product, just means our primary drying now runs unnecessarily long. Our product is already relatively dry and it's just kept at a low temperature. Since primary drying is the most expensive and time-consuming step, that in the end means especially loss of time and money, which goes well with the title, of course, of the webinar. Now, the opposite is scenario 2. We have an early change to secondary drying. Now, that means we still have a high residual moisture content in our sample, which usually results in a lower glass transition temperature, lower collapse temperature as well. And in general, we have a higher molecular mobility now in our sample. Since we usually use freeze drying to have a drying technique with a low molecular mobility, this usually facilitates some instability in most samples. For example, we might have a collapse or loss of shape, or when we talk about biopharmaceutics, typical instabilities here would be degradation, denaturation, and aggregation. So what can we do? And of course, we need to implement a way to detect the endpoint. And the traditional way here is temperature control measurements, and it's still used in almost all systems. And the idea is that the sample temperature, which I think most of you know, during primary drying is below the shelf temperature, because sublimation is an endothermic process, and that lowers the temperature of the sample, essentially. Once the sample is dry, however, there's no more sublimation happening, and therefore at the primary drying endpoint, the shelf temperature should be the same as the sample temperature. Now, there are some issues that are connected to this temperature control measurement. For example, the sensor, which you can see here, cannot always be placed properly. And this is especially the case when we have a solid sample instead of a liquid sample, because in a solid sample, of course, it's harder to place a thermocouple, essentially. Also, the measured vial might not be representative for the batch. Here, the rule of thumb is that usually the measured vial dries faster compared to non-measured vials. And also, we might have an error by the operator due to a wrong placement of the sensor. You can see here how it should be placed on the bottom and in the middle of the vial, because that is the point that is considered the one that dries the last. However, because the sensor usually is flexible, it's actually not that easy. So therefore, there are also other techniques, and one that is very important is comparative pressure measurement. Now, the idea of comparative pressure measurement is that we have two types of manometers. We have a capacitance manometer, which you can see here. So the core element is this diaphragm and an electrode, and they are at a certain distance to each other, which determines the capacitance between those two. Now we have a measurement site with the changing chamber pressure, and we have a constant reference site, which has a pressure close to vacuum. What happens now when we change chamber pressure is the diaphragm shifts, the distance between the two elements changes, and therefore we have a change in capacitance, which you can use to measure the pressure. Now, what is very important here is the capacitance manometer is actually independent of gas composition. And that's why it's also usually used to generally control the freeze drying cycle or the pressure progression during freeze drying. Now, the other manometer is a Pirani gauge. And a Pirani gauge, you can see here, is essentially a tube with a heated wire, and the wire is heated by a current that's flowing through there. And the idea is that this wire now loses energy to the surrounding area by collision of gas molecules, which then results in a change in resistance, and ultimately results in a change in the current that's flowing through there. Now, how does this measure pressure? Well, the collision rate is dependent on the chamber pressure, because of course the higher the chamber pressure, the more molecules we have in the atmosphere, the higher is the collision rate. What's very important though is that this heat loss, or this loss of energy to the surrounding media, is also very dependent on the gas heat conductivity, and therefore it's dependent on gas composition. Now, how do these two work together? Generally, a Pirani gauge is calibrated in a pure nitrogen environment. That means only in a gas that has the same heat conductivity as nitrogen, the Pirani gauge will display the real pressure. However, during primary drying, because the sample sublimates water vapor in the air, the atmosphere consists almost 100% out of water vapor, and water vapor, as you can see here, has a heat conductivity compared to 1.6 times the one of nitrogen. Now that results in a difference between the two manometers of about 0.6 times the chamber pressure, which you can see here. Now, when the sample dries, of course, there's no more water vapor going to the atmosphere. The gas consistency changes from 100% water vapor to 100% nitrogen, and the Pirani gauge, so to say, falls back into its calibrating conditions. And therefore, ideally, when the sample is dry, the Pirani gauge and the capacitance manometer should display the same pressure again, which then determines our endpoint. Now, we're going to have a look at how this looks in a real freeze drying cycle on a slide after the next one. Before that, what are the advantages of comparative pressure measurement? Well, the most important one is it's dependent on a complete batch and not just on one sample, because essentially all samples contribute to the water vapor in the atmosphere. Also, it's non-invasive, which enables us to also dry and measure unconventional samples, which again usually are solid samples like fruits and books, which are all samples where freeze drying is used. And also it's we have no error due to any wrong placement, like with the thermocouple. Okay, so, and now we kind of switching towards finding a good endpoint criterion. So here you can see my first test system, a test run. And as a test system, I used the glycine solution, which is of course liquid and also a rather simple system. As you can see, the two lower curves display the pressure sensors, the two upper ones the temperature sensors. As you can see, more or less at the same time point, those two converge. And if you think back now, that determines our endpoint, so this means our sample is dry now. When we now think of how do we want our endpoint criterion for comparative pressure measurement to look like, we would say, okay, it looks like when the chamber pressure and the Pirani gauge are the difference between those two is 0, we reach our endpoint. However, when we zoom in, we see there's a lot of fluctuations happening. Also, the two manometers in this case do not converge perfectly, merge perfectly. And therefore, when we determine this difference of 0, we risk that our endpoint will never be reached due to those fluctuations. So what I did is, I had a look at the fluctuations once the Pirani gauge stabilized again. And I had a maximum difference of approximately 0.02 millibar, which already was relatively high. Actually, this was, so to say, the worst freeze-drying cycle, which why I then took it as a reference, sort of as a worst-case scenario. So when we now think of an endpoint criterion, we know this pressure difference has a lower limit of 0.02 millibar, because once we go below this, we're sort of in a noise region of the sensors, and we risk that our endpoint will never be reached. And the question is, what is the upper limit now? But also, what's important to understand is that the endpoint criterion is not just determined by the pressure difference, but also by a waiting period, which essentially ensures that our pressure difference is not just reached due to any fluctuations. And to determine, I was more concerned about finding a good endpoint criterion as far as the pressure difference goes, and therefore, for now, I kept a waiting period constant of 1 hour. Okay, so what I then did, again, I took glycine solution as an easy, simple test system. I set the process pressure constant to 0.3 millibar, and I used the L200 from lyoVapor from Büchi. And I also determined two criteria I want to have in order to determine whether I have a good endpoint criterion or not. One is quite obvious. Of course, I wanted the pressure sensors to converge before the switch to secondary freeze drying happens. But also, since I have a simple system here, a liquid system where the temperature measurement should work, I also want the shelf and the sample temperature to converge before that happens. And I'd also like a safety margin in between criterion 2 and 1. And I then tried different pressure differences. And you can see I used the 5% glycine solution. You see the best result I had for a pressure difference of 0.025 millibars, so very close to this noise limit I mentioned earlier. To then sort of ensure that this actually works, I repeated this and I used a slight variation. So I had a glycine solution of 10%, not a big one though. So it still worked, however. So at that point, I was relatively confident that for the simple system, this comparative pressure measurement endpoint works quite well. So what I then wanted to do is I wanted to sort of test the limits and wanted to try a relatively complex system. And what we came up with were actually strawberries. Because first of all, they are solid, so temperature control measurement does not necessarily work here. And also they're very heterogeneous because they're different in shape and size. And you can see the result here. As you can see, I still have a temperature curve. And what I did here is I placed the sensor in the middle of the largest strawberry, which I thought was the one that probably dries the last. And it actually worked quite well, as you can see, at least for primary drying. Also, the whole cycle took 2 days, so over 2 days actually, so relatively long. And we see sort of this constant decrease in the Pirani gauge and the pressure progression here. And because of this long freeze drying time and this constant decrease, I was kind of anxious that the waiting period of 1 hour might be too short. However, when we think of the criteria on the slide before the last one, actually it still works very well. The temperature sensors and the pressure sensors merge more or less at the same time point. So at that point, I was relatively confident, and I sort of was confident that the endpoint criterion is established. Okay, so now let's switch to secondary drying, because when we have a closer look in the Pirani gauge development progression over during secondary drying, we see there's a small peak, and this actually shows us that there's a secondary drying event happening. And what's interesting is this was not visible in the temperature measurement, which you can see here. And in fact, the temperature endpoint was never reached because for some reason the temperature of the sample didn't rise. And this is not probably because it was not placed properly in the solid sample. So this also shows an additional advantage of the whole comparative pressure measurement, because of course you have a new variable you can look at that tells you more about the freeze drying cycle. So it's not just an endpoint determination technique. So when we think about an endpoint that we want to implement here, we see the pressure difference was really low. So it actually was just 0.027 millibar, so very close to the noise floor. And that's actually something we should expect during secondary drying, because there's only a low residual moisture content in the sample. Therefore, we cannot expect the Pirani gauge to go back up to its full 0.6 times the chamber pressure, because the atmosphere will probably not switch back to 100% of water vapor. So what does this mean for the endpoint? Well, first of all, we cannot necessarily use the same criterion for primary drying and secondary drying. For secondary drying, however, I think in general it's always better to increase the waiting period instead of further decreasing the pressure limit, because the pressure limit already is usually very close to the noise ratio, the noise floor. So by further decreasing it, of course, we're risking going closer to the noise, and then we're again risking that our endpoint will never be reached due to those fluctuations. So better increase the waiting period a bit here. Okay, so now we're almost at the end. That's the slide before the last one. So some last points to consider. Especially for the Büchi system, it's important to do a vacuum test before each run, because that recalibrates your Pirani gauge. Do that also at the drying conditions, so at pure nitrogen or air, so that later during drying, the Pirani gauge falls back into its calibrating conditions, as you can see here. Also, Ulrike talked about one cycle for all. Now, when we think about one criterion for all cycles and samples, now let's start with samples. So the endpoint criterion I developed was sort of usable for very simple systems like Glycine solution, but also the rather complex strawberries. So at this, so generally it looks like it's like you can use one criterion for different samples. However, keep in mind that when you have a sample that dries very slowly, that increases your whole freeze drying time, it might be good to increase the waiting period. Again, it's probably better to not change the pressure limit too much, because again, you're risking going to the noise level and that your endpoint will never be reached. So better increase your waiting period here. And when we think about one criterion for all cycles, that's very important when you have different pressures, that the maximum difference between Pirani gauge and capacitance manometer is always this 0.6 times the chamber pressure. So it's highly dependent on the chamber pressure. And that means that when you have actually a different chamber pressure, you might need to consider changing this pressure limit again, at least do a dry run with the already established endpoint criterion, and then have a look on how it changes. Okay, so now we're almost at the end, just some key points. So comparative pressure measurement uses 2 manometers, capacitance manometer, and a Pirani gauge. And the working principle is we have this difference in the heat conductivity of the surrounding gas during primary drying and then once the sample is dry. There are 2 parameters we need to think about: the pressure limit and the waiting period. And now sort of the workflow when you purchase, especially when you purchase a new system, you should start with a simple system and find the noise limit. Generally, sort of get a feeling how the different variables progress over the drying time. Then of course you should start thinking about your criterions. What are the criterions you want in order to say we have a good endpoint now? Also, one I didn't really mention here, very important one, of course, is the residual moisture content in the end in your sample. Now, for the glycine solution, especially after secondary drying, there was not a lot of residual moisture left, so it was far below 1% there. However, for other samples, you might think about this, thinking about this as well. Then try different criterions, find the best criterion for a simple system, and then you can go on to check with more complex samples, of course, also the samples you eventually want to dry anyways, and then of course implement the criterion in the end. So that was my part of the webinar. Thank you all for listening, and I'm still sticking around for further questions.
Thank you, Moritz, for these very useful insights. Now we've already received several questions, and I'd like to share them with our panelists. The first one is for Ulrike. You mentioned that the higher pressure will speed up the freeze drying process. But what is actually the maximum pressure that can be used, and what is maybe the ideal pressure that can be used?
That often very much depends on the sample. As we said before, there's always to think about the collapse temperature, and in principle, you could go up to 5-6 millibar, just below the trigger point, but then there is always the risk of the sample melting. We normally work somewhere between 0.5 and 1 millibar for our samples. However, I have already also gone way below to 0.08 if the sample was had a very low collapse temperature.
Okay, thank you very much for Ulrike. Then we have a question for Moritz. You mentioned that the freeze drying run of the strawberries was untypical because of the constant decrease in the pressure. What do you think might be the reason for that?
Yeah, so there might be different things that could happen here. So one thing, of course, is we have a biological sample, so we're having probably a higher resistance, like a higher product resistance due to the biological matrix. So that in general slows down the process. In general, this decrease means that the drying process is slowed down significantly. And also, because we have heterogenic samples and they all have a different size, probably some smaller strawberries or smaller samples dry faster, so they're already dry, and therefore just the large samples contribute to the atmosphere there. So that's why I think we have this constant decrease. It's also not completely untypical that this happens. So this might happen, especially when you have heterogeneous samples.
Okay, thank you, Moritz. May I just throw in? So you mean that the more homogeneous the sample would be, the more accurate the endpoint determination method will be?
No, not necessarily, because ideally you have an endpoint criterion in the end that, of course, is robust against these variables. As I said, when you have this constant decrease, it's probably better to just increase the waiting time a bit. So you make sure that when your endpoint limit, when your pressure limit is reached, that you then have a longer waiting period because of this longer, slower decrease. But that not necessarily limits your endpoint determination method. Yeah.
Okay, thank you very much. Then I have another question for Ulrike. You mentioned secondary drying. When should secondary drying be done? And is it done in every cycle or just in specific ones?
It isn't done in every cycle. However, it should be done when the dryness of the sample is very important, or when it is known that the sample does not, will form a lot of crystal water and might actually not lose enough water in the primary drying. then I would always say put on a secondary drying phase, and it's best to try a few phases, try a few times, how long you want to do it, and measure the moisture content, especially in biological samples, to get essentially the moisture content that is best for the biological active.
Okay, good. Then I have another question for Moritz. Instead of taking the pressure difference, why not just take the Pirani gauge progression as an indicator and determine the endpoint by looking when it stabilizes again after it drops because of the change in gas composition?
You can do that, and it's actually sometimes done. However, now we can again think back to the strawberries when we have like a situation where you have this constant decrease. And we didn't really see like this sudden drop. We had like a constant decrease. So depending on how exactly the algorithm essentially is to figure that out, this drop, this might actually be a problem there. But it's done sometimes. But I think the pressure difference works equally good. And especially for this constant decrease, there is a sort of advantage when you just look at the pressure difference. Yeah.
Okay, thank you very much. Then I have another question for Ulrike. So why is it even needed to heat the sample with shelves? And what happens if there are no shelf heaters available?
So it is not needed to heat the samples with shelves. However, it will decrease the time that the process runs. So it can save you hours in a freeze drying process. If it is not possible to heat it, as seen with flasks that can't be put on a shelf, there's always the energy you have from your environment anyway, so from radiation, from the sun, and then the process might just take a bit longer.
Okay, so it basically just speeds up the process.
Yes, it will speed up the process significantly.
Okay, and then I have one more question for Ulrike. So why does a sample even need to be pre-frozen, or can I put my sample in unfrozen?
The sample, if the sample is being put in unfrozen, and we go down with the pressure, it will still freeze, but it will boil and splash before, so there is no homogeneous freezing. It might not even freeze completely, depending on the depth of the sample. So I would always, it is really important to make sure it is frozen, and it's really also important to make sure it is properly frozen, because otherwise during the freeze drying process the sample will melt, and then essentially it's not usable anymore what you get out of the freeze dryer.
Okay, and then one question for Moritz. The presentation is only about water-based systems. Can comparative endpoint detection also be used for organic solvents?
Yeah, so in general it can. The whole limitation is actually you need a solvent with a high enough heat difference to the heat in the heat conductivity compared to nitrogen. But otherwise, of course, you can also use other systems. However, the only thing is what you need to keep in mind, you have a heated wire as a central element in this Pirani gauge. And of course, when you have a highly explosive or flammable solvent, this might be a problem. So sort of the best practice here is to first suck the vacuum, and once you have your vacuum, there's no more oxygen in the air anyways for any explosion to happen, and then switch on the Pirani gauge. But otherwise, there's not really it's not really limited to just water as a solvent.
Okay, thank you very much, Moritz. And then one last question for Ulrike. Is it better to employ a fast or slow freezing step to achieve small volumes and powder-like product at the end?
The speed of freezing will determine more the porosity of the finished product. So if you freeze slowly, you will have more and bigger pores in your sample later, because the ice crystals can form better and grow bigger, while small freezing will give less porous structures with smaller pores. I would probably think that faster freezing will give a nicer powder, but this one I would have to look up essentially in literature further.
Okay, thank you very much, Ulrike. So we received so many questions that unfortunately we do not have enough time to answer them all. But we will collect all the topics and we will do our best to give you answers to all questions for our several channels. For this reason, we invite you to follow us on Bart's blog, on our LinkedIn profile, to stay updated on freeze-drying topics of interest and much more. Any further questions that you might have, you can please write them directly to marketing@buchi.com. Marketing@buchi.com, and Buchi is BUCHI.com, or interact with us through our social media channels. In the next few days, you will also receive a follow-up email with a link to the recording of today's session, so you will receive all the slides and all the spoken words of today's session. On behalf of Buchi Labortechnics and our presenters, we thank you very much for joining us today, and we wish you a pleasant day, and we wish you good health in these very special times. We hope to be in touch with you soon again. Thank you very much. Have a good day. Bye-bye.